Hello friends. In the last class we were looking at the mixing length model and the eddy viscosity model for turbulent flows. So we said that the Reynolds stresses that we get by time averaging of the Navier-Stokes equations, splitting them into the mean component and the fluctuating component, and then putting them back into the equations and time averaging the equations. So when we do that to the momentum equation, we get additional stress terms. So if I do look at the three-dimensional equation, I'll get three additional stress terms in each direction. Okay. When I reduce it to the two-dimensional case, I get two additional stresses in each direction. So in the 2D equations, we found that we had the U prime squared bar, then U prime V prime bar, then you had the V prime squared bar, right? So the U prime V prime bar and the V prime U prime bar are both present. Now, when we cast them back into the equation, we find that these terms actually constitute additional diffusion term or additional viscosity term. And so we represent them by what is called the turbulent eddy viscosity. And similarly in the energy equation by eddy diffusivity, or the thermal diffusivity alpha, which is a molecular diffusivity, is augmented by another eddy diffusivity alpha T. And similarly the momentum diffusivity or the kinematic viscosity nu is augmented by an eddy viscosity term nu T. Now, how do we estimate this? There are several ways in which it has been modeled in the literature. The most original or the first one was due to Prandtl, who said that when there is an eddy movement, then there is a certain length scale over which the fluid that moves preserves its identity before it mixes with the rest of the flow. So that length over which the fluid in the eddy retains its identity is called the mixing length. And we argued in terms of a fluid layer at Y and Y minus L constituting an eddy. So we said that the fluctuation it causes U prime is of the order of L times del U by del Y or del U bar by del Y. And we wrote both U prime and V prime in that fashion, and therefore we identified an expression for the eddy viscosity which looked like kappa square Y square, right? So as you go from the wall, the eddy viscosity increases as Y increases, and as you go closer to the wall, the eddy viscosity decreases further as Y decreases. So this is basically what we wrote, and with that we were able to write the expressions for the eddy viscosity. So in today's class, we will build up on top of whatever we discussed in the previous class and derive an expression for the velocity profile in the boundary layer and therefore the shear stress at the wall and the skin friction coefficient, and similarly the temperature profile in the boundary layer and therefore the Nusselt number or the Stanton number, which is Nu by REPR. So we will be looking at these terms in today's class. So we basically tried to understand even in the last class that you can look at the boundary layer in terms of the near wall region and the far away region. Okay, so already the mean flow, that is the flow over the flat plate, we divide it into the boundary layer and the free stream. Now within the boundary layer in turbulent flow, we divide it into multiple parts, the near wall region and the far away region. So the near wall region is the wall region, it's called the wall region, and it is governed by what is called the law of the wall. And the far away region, which is towards the edge of the boundary layer, is called the faraway region or the wake region because it participates in the free stream eddies, and therefore it is more in the form of wakes of the free stream, and therefore it is in the wake region. So you have the wall region and the wake region, and within the wall region there is a very small region which is called the laminar sub layer. Okay, the sub layer where the flow behaves like laminar flow, where it is viscosity dominated and the turbulence is very small or absent. So nu is much larger than nu t, or alpha is much larger than alpha t. Okay. And we also said the near wall region where the inertial terms can be small or negligible, you get the shear stress equal to the wall shear stress for a certain distance. And we said that when we go away from the wall into the wake region, this diminishes because the velocity gradients themselves diminish, and therefore eventually becomes zero at the edge of the boundary layer. Okay, so we looked at the structure of the wall boundary layer as the inner layer and the outer layer. So let's go to the whiteboard and start looking at that again. Okay, so suppose this is the flat plate, okay, and there is a turbulent boundary layer that is on top of it. This we normally divide it into the inner layer or the wall region and the outer layer or the wake region. So this inner layer or the wall region is characterized by the inertia terms close to zero. What are the inertia terms? The equation looks like, let's say, u bar del u bar by del x plus v bar del u bar by del y. This is the left hand side. In the boundary layer equation on the right hand side, the pressure term is absent. You get del by del y of nu plus nu t into del u by del y, del u bar by del y. Okay, so in the near wall region, we said the inertia terms are zero, which basically means these terms are negligible in near wall region. Which really says that then del by del y of this is also of the order of zero, or what is there in this is a constant. So nu plus nu t into del u bar by del y is independent of y. So what we say is, in this region, if I draw a profile of shear stress, then suppose the shear stress at the wall is tau wall. So this remains equal to tau wall more or less throughout this region. After that, it vanishes or diminishes and eventually goes to zero at the edge of the boundary layer. So here it goes to zero, right? So that is the concept that we talked about. So we said that in the inner region, the shear stress is nearly constant and equal to tau wall. So this is nu point of y and this is equal to tau wall by rho. Okay, because this is nu and not mu, so this is tau wall by rho. So this is the understanding that we had, and in the inner layer itself, we said that very close to the wall, we have nu much greater than nu t, and in the other region, nu t is much greater than nu. So then the first term is important in the viscous sublayer. We call it the viscous sublayer. And this region, which is the core region, turbulent core region. Okay, so in the viscous sublayer, nu is much greater than nu t, and in the turbulent core, mu T is much greater than mu. So we say that the viscous forces or the laminar viscosity dominates over the turbulent viscosity in the viscous sublayer, and the turbulent viscosity dominates over laminar viscosity in the other layer. So that is basically what we talk about, and this continues to be true of this region as well. So that is why in the entire turbulent core, not just the other part of the inner layer, but also the outer layer, this is valid. Okay, so now when I use that in this one, I will be able to get two velocity profiles for these two regions, which is what we were writing in the previous class. Okay, so let us do that clearly now. So mu plus mu T into del U bar by del Y is equal to tau wall by rho. Okay, so this is the thing for inner layer. So now in the viscous sublayer, where mu is much greater than mu T, I can say mu del U bar by del Y is equal to tau wall by rho. Now this I can actually write it in terms of the wall coordinates. So in the turbulent boundary layer, we use what is called the wall coordinates. What is wall coordinate? You normalize y and u with respect to the shear velocity and the viscosity. So we define shear velocity u star is equal to square root of tau wall by rho, okay, or rather tau wall is written as rho times u star square. Okay, so this is basically the way shear velocity is defined. So then in the wall coordinates, you define u plus is equal to u bar divided by u star, okay, and y plus, which is an orthogonal y coordinate near the wall, you define it as y times u star by mu. Okay, so this is in some form so Reynolds number with respect to y as the coordinate. So you define it in this fashion, then this equation becomes mu plus mu T multiplied by du plus by dy plus, and this u plus would have a u star here, and this y plus would have a mu by u star, so this equals u star square. This is equal to tau wall by rho, which is again u star square, right? Because you defined u star as tau wall by rho square root, so tau wall by rho is u star square. So if I cancel out the u star square on both sides, then I get a nu plus nu T by nu. So this I'll write it as 1 plus nu T by nu into du plus by dy plus is equal to 1. I write it as total derivative because the dependence on x is absorbed into this u star, because this u star is a function of tau wall, which is a function of x, and therefore this u by u star and y u star by nu take away the x dependence of this whole thing, and this becomes a total derivative in y plus. Okay, so this is your boundary layer expression. So once you have done this, if I write it in terms of u plus and y plus, this actually becomes the nu T by nu is extremely small, and therefore it will be du plus by dy plus is equal to 1. Or if I integrate this, I get u plus is equal to y plus plus constant. And we know that at y is equal to 0 or y plus equal to 0, u is equal to 0 or u plus equal to 0. Okay, so in which case the constant becomes 0. So in the viscous sublayer, you have u plus equal to y plus. So this is one part of the boundary layer velocity profile. So in the viscous sublayer region, which I drew here, in this small region that I have shown here, you have a velocity profile which is u plus equal to y plus. Okay, so that is your viscous sublayer. Then in the remaining region, that is turbulent core, where nu t by nu is much greater than 1, or nu t is much greater than nu, then this first term would become negligible. So nu t by nu into this is this. So du plus by dy plus is equal to nu by nu t, right? So this is the expression that you would get. And for nu t, we will substitute from the model of mixing length. So in the mixing length model, we had written that where is the mixing length model? Just a moment. Yeah. So nu t we had written as this. So k kappa square y square into modulus of del u by del y, right? So that is what we wrote. So let's substitute that here. So this will be equal to okay, for nu t by nu, I can substitute kappa square y square into du plus by dy plus the whole square. Okay, and this y also would become y plus square. Okay, so let me write that completely, and then we can okay, nu t is equal to kappa square y square into du by dy. Okay, now this, if I write it in terms of the normalized coordinates, it will become kappa square into y plus square multiplied by u star square by mu square by u star square. Okay, multiplied by, then there is another u star for this one, so there is a u star square by nu into du plus y dy plus, because u star into u star u plus is u, and y star into nu by u star is y plus. So this is so when I write this u star square gets cancelled, one nu goes away. So you get nu t is equal to this. So nu t by nu becomes equal to this, nu goes to the other side. You get kappa square y square into du plus by dy plus 1 is here, multiplied by another du plus by dy plus from this equation, because there is nu t by nu multiplied by du plus dy plus. So this will be du plus by dy plus the whole square. This is kappa square y plus square, this whole square equal to 1. Okay, and so nu t by nu into du plus by dy plus is equal to kappa square y plus square multiplied by du plus by dy plus. So now what happens? Du plus by dy plus is equal to equal to 1 over kappa y plus. Okay, so this is what you get. So you can integrate it now. So this becomes du plus is equal to 1 over kappa dy plus by y plus. Okay, so if I integrate this from viscous sublayer, so y plus at viscous sublayer to any y plus in the core region, this will become again integrated from y plus in viscous sublayer to y plus in the core. So what are we doing now? We are integrating it from in this region. So from the viscous sublayer to any location inside this, we are doing the integration, because we know that here it is u plus equal to y plus. In the remaining region, I am integrating it from this. So if this is y plus at viscous sublayer, okay, this is y plus equal to 0. So from 0 to viscous sublayer, u plus equal to y plus, and from y plus onwards, y plus viscous sublayer upwards, it is the other expression. So we know that at y is equal to, or y plus equal to y plus of viscous sublayer, the u plus equal to y plus is valid. So u plus is equal to y plus of viscous sublayer. Okay, because u plus equal to y plus. So if I do that, then I get this expression as u plus at any y minus y plus viscous sublayer. Okay, so this is the left hand side when I integrate. On the right hand side, I would have log of y plus minus log of y plus at viscous sublayer into 1 by kappa. Okay, this is the thing that you get. Okay, so now the expression for this will be, then you can this can go to the other side. U plus would be equal to 1 by kappa log y plus y plus VSL minus log of y plus VSL. Now both of these are, in some sense, they are a constant, and so you have this in the form of a log y plus b. Okay, so this is the way it is, where a is 1 by kappa and b is this term. Okay, so this is the second equation, which is valid for the turbulent core. So we have got a velocity profile that is valid for the turbulent core. Now this is valid all the way up to y is equal to delta. So at y is equal to delta, you get u plus is equal to actually u infinity divided by u star, right? Because u goes to u infinity at y is equal to delta, and that is equal to 1 over kappa log of this y plus is delta times u star by mu. Okay, plus this is a constant b. Okay, so that is the way it is coming. Okay, so this is the expression that I would have. So using this, actually, I can eliminate the u star or term wall from the other equation to get the velocity profile. So we'll do that by using this velocity profile. The velocity profile for the whole boundary layer, according to Prandtl, is u by u infinity is equal to y by delta whole to the power of 1 by 7. This is the velocity profile that is defined. This, we can say, is clearly valid for the core region of the boundary layer, but not in the viscous sublayer. So viscous sublayer, the velocity profile will be different, but this is for the core region. So equations 1 and 2 together. This is the equation number 2, which is 1 by kappa log y plus this one. And the equation 1 is u plus equal to y plus in the viscous sublayer. These two together is called the law of the wall. Okay, and this is the boundary layer velocity profile that is given for turbulent boundary layers by Prandtl. All of these are obtained by fitting curves to the experimental data. So if I plot the experimental data as let us say this is y plus plotted on a log scale, so 1, 10, 100, 1000, and this is, let's say, 10, 20, 30, etc. Then you get a profile which looks like a straight line in these regions, and here it goes more like a curve, because u plus equal to y plus on the log scale looks like this curve, and this is your straight line region where there is a 1 by kappa slope of this log. So the u plus gives something like 2.5 log y plus 5.5. So this is your A and this is your B for this region. Okay, and in this region, this is u plus is y plus. So this is in the core, and u plus equal to y plus in BSL. So if I equate these two, this is equal to this in the sublayer region. So then you get y plus VSL is a location where both of these profiles are equal. So that you get somewhere here. You get this y plus VSL is approximately 11.6. Is what you get. Okay. So if I substitute this, A is equal to 1 by kappa. So then you get the kappa is equal to 0.4. Okay. So these are the profiles that you get from the plotting of the velocity profiles, the experimental measurements. So these values you can take for the law of the wall that is written. So the law of the wall now can be summarized as in the viscous sublayer u plus equal to y plus, and in the core region it is 2.5 y plus 5.5. This is the law of the wall. Okay. Now if I go with this expression, that is the 1/7 power law, which I just wrote, u by u infinity is equal to y by delta to the power of 1 by 7, and write the momentum integral equation for the boundary layer. So momentum integral equation is very similar to what we wrote in the laminar flow. You start with this equation, and you write the integral for the boundary layer. Then you get d by dx of integral from 0 to delta of u bar into u infinity minus u bar dy is equal to the wall by rho. This is the expression that you get. This is the same as what we got in this one. And this the wall by rho is actually nu plus nu t into so at the wall, this is del by del y at the wall. So this is the expression that you get, exactly the same expression as we got in the laminar sub layer, except that laminar boundary layer, except that this u is replaced by u bar. So now if I take out u infinity square and write it in the form of non-dimensional form, so I'll write a u infinity square, then u bar by u infinity, and this whole thing by u infinity. Then what do I get? This I get as y by delta raised to the power of 1 by 7, and this will be 1 minus y by delta raised to the power of 1 by 7. Okay, and if I write this as d of y by delta, then I get a delta that multiplies this, which can come out of the integral because this delta is independent of y. So you get a d by dx of delta and integral from 0 to 1, because now y by delta is 0 to 1 of this whole thing into u infinity square is equal to tau wall by rho. Okay, so this is the expression that you get. Now if I integrate this y by delta, if I call it as eta, then I get eta to the power of 1 by 7 into 1 minus eta to the power of 1 by 7 d eta from 0 to 1. If I integrate this, I get a number which is 7 by 72. Okay, you can do this integration and check. So you will get eta to the power of 1 by 7 minus eta to the power of 2 by 7. So it will be eta to the power of 1 by 7 plus 1 by 1 by 7 plus 1. So it is eta to the power of 8 by 7 by 8 by 7 minus eta to the power of 9 by 7 by 9 by 7. So you will get a 1 by 8 minus 1 by 9, or 7 by 8 minus 7 by 9, which will be 7 by 72. That's what you will get in this expression. So if I substitute that here, then I'll get a 7 by 72 u infinity square that can be taken out of the d by dx because u infinity is independent of x for a flat plate boundary layer. Then I get a d delta by dx on the left hand side, and that should be equal to the right hand side, which is tau wall by rho, okay, which is actually equal to u star square. Okay, so this is the expression that I have from the integral equation, and in this, if I take this condition, which is at the edge of the boundary layer, okay, where I use an expression. So if I take this expression and can normalize it, can write it in terms of this one, then I get in terms of u plus and y plus, I get u plus is equal to 8.75 y plus raised to the power of 1 by 7 is the expression that I would get. Okay, so if I use that expression and eliminate, so if I use this expression for this is u by u star is equal to 8.75 into y into u star by nu whole thing raised to the power of 1 by 7. So if I substitute at y equal to delta, this becomes u infinity by u star, and this becomes delta. Okay, so if I substitute for this expression, okay, so if I substitute for u star from this expression into this one, then I'll be able to eliminate the u star. Okay, so if I eliminate the u star, I get a differential equation in delta, and I can solve for the delta from that equation. So if I do that, what do I get? I get okay, so u infinity divided by u star is equal to 8.75 multiplied by delta u star by nu whole to the power of 1 by 7. So from this, if I can isolate u star and take all the other terms to the other side, I get this gives me u infinity divided by 8.75 multiplied by nu to the power of 1 by 7 divided by delta to the power of 1 by 7. Okay, so all of these terms are taken. So here I have u star to the power of 1 by 7, and there is a u star here. So this will be equal to u star raised to 8 by 7. Is that correct? So now if I write an expression for u star from this one, so u star will be equal to u infinity into nu to the power of 1 by 7 divided by 8.5 into delta to the power of 1 by 7 whole to the power of 7 by 8. Is that correct? So now this I can take out the delta from here and write it outside. So if I take the delta out from here, this is delta to the power of minus 1 by 7 into 7 by 8. This will become delta to the power of minus 1 by 8. Okay, so this is the expression that I get. Now I substitute for u star into this equation. So this equation basically has u star square is equal to 7 by 72 u infinity by d delta by dx. So u star square is equal to this whole thing raised to 7 by 4 u infinity into nu to the power of 1 by 7 divided by 8.5 raised to 7 by 4 into delta raised to minus 1 by 4, and this would be equal to 7 by 72 into d delta by x into u infinity square. Okay, so now if I rearrange this into a differential equation in delta and solve it, I'll get delta to the power of 1 by 4 d delta is equal to, okay, so I take this delta to the right hand side, so I get delta to the power of 1 by 4 d delta, bring all the rest to the left hand side. Then what do I get? I get so this is u infinity raised to the power of 7 by 4, and this is u infinity square, which is u infinity to the power of 8 by 4. So if I bring it here, so it will be minus 1 by 4. So there will be u infinity to the power of 1 by 4 in the denominator. So I can take this 1 by 8.5 raised to the power of 7 by 4. Then there will be this nu to the power of 1 by 7 into 7 by 4 is nu to the power of 1 by 4, and this u infinity, there will be a u infinity to the power of 1 by 4 when this u infinity square comes to this side, and there will be a 72 by 7. Okay, so now what do I do? This will be equal to, so if I integrate and this into dx. Okay, so all of this is a constant with respect to x, and therefore they can be retained as it is. And I also know that at x is equal to 0, delta equal to 0. So there will be no integration constant that will come. So if I integrate this, I'll get delta to the power of 5 by 4 divided by 5 by 4 is equal to this whole thing in the bracket multiplied by x. Okay, so now what do? I write this as this is x to the power of 1. There is a Reynolds number term that will come here if I get an x to the power of 1 by 4 in the denominator. So I'll write it as x to the power of 5 by 4 divided by x to the power of 1 by 4. So what do I get? This x to the power of 5 by 4 will come to this side, and the 5 by 4 I can bring to this side. So I'll get delta by x whole to the power of 5 by 4 is equal to 5 by 4 times this x to the power of 1 by 4 will go inside. So I'll have a 1 over 8.5 raised to the power of 7 by 4 into 72 by 7. All of these terms are constant, multiplied by nu to the power of 1 by 4 divided by u infinity to the power of 1 by 4 and x to the power of 1 by 4. So now this whole thing actually becomes 1 over REX to the power of 1 by 4. Okay, and this whole thing, if I evaluate, it comes to something like 0.28 something. Okay, So now I want the delta by x in terms of this. So the whole thing I raised to the power of 4 by 5. Okay. So then this raised to the power of 4 by 5 will give me a 0.37, and this REx to the power of minus 1 by 4 raised to the power of 4 by 5 will become minus 1 by 5. So I'll get this implies delta by x is equal to 0.3703 into REx raised to the power of minus 1 by 5. So this is the expression that I get from this derivation, and using this expression I'll be able to then write the expression for the shear, the skin friction coefficient CF. Okay, so skin friction coefficient CF is CF by 2 is tau wall by rho u infinity square. Okay, and this, if I substitute from the other expression, the tau wall by rho u infinity square, the tau wall by rho u infinity square is actually coming from here. This u star is nothing but tau wall by rho, and so u star by u infinity. U star by u infinity is the square root of tau wall by rho u infinity square. Okay, so u star square is tau wall by, because u star square is tau wall by rho, so this divided by u infinity square is this by u infinity square. Okay, so this u infinity square, if I bring it to this side, then I'll get the u star by u infinity square star. So this term divided by u infinity square, so this will be equal to this term divided by u infinity square. So it will be okay, I can simplify it from here. I will not write this expression in more detail, so I'll just bring it from there, and so I'll get 1 over 8.75 raised to the power of 7 by 4 multiplied by mu by u infinity delta whole to the power of 1 by 4. This delta, I write it as x into delta by x. So then I'll get 1 over 8.75 raised to the power of 7 by 4 multiplied by REx to the power of minus 1 by 4 into delta by x, again raised to the power of 1 by 4 minus 1 by 4. Okay, so this will be CF by 2. And if I substitute for delta by x as 0.3703 into REx to the power of minus 1 by 5, so this raised to the power of 1 by 4 will be 1 by 20, and the 1 by 4 minus 1 by 4 plus 1 by 20 will actually give me again 1 by 5. So this actually would give me a value which is 0.0288 multiplied by REx to the power of minus 1 by 5. Okay, so this is the expression for CF by 2, or CF will be 0.0576 REx to the power of minus 1 by 5. So this will be your expression for skin friction coefficient, and accordingly you will be able to get the viscous term. So this is the fluid mechanics result for this problem. Now we need to write the temperature profile and get the heat transfer result. So in order to write the temperature profile, what do? We write the energy equation in the inner region, the inner layer energy equation. The inner layer energy equation would be again the inertial terms getting cancelled out. So the u bar del t bar by del x plus v bar del t bar by del y, the advection terms, these will be negligible. This will be del by del y of alpha plus alpha t into del t bar by del y. Now, if this is negligible, then this also becomes close to 0, which gives me alpha plus alpha t into del t bar by del y is equal to the constant, which is equal to minus q wall by rho Cp. Because it is k by rho Cp, the rho Cp will come here. So the q wall by rho Cp will be equal to this. This is the same way as we wrote for the inner layer for velocity. We will be writing this in terms of this. So if I look at this one in the non-dimensional terms, if I write it in terms of y plus, so I'll get alpha plus alpha t multiplied by del t by del y plus. If I write this, y plus will basically give rise to a nu and u star that will come here. This will be equal to minus q wall divided by rho Cp. So what will I do? I'll take this rho Cp and q wall to this side and this alpha plus alpha t by nu to the other side. So then I'll get rho Cp u star, okay, divided by minus q wall, okay, and this t I will write it in terms of t minus t wall. So into del of t bar minus t wall divided by del y plus. Okay, so now this will be equal to 1 over alpha by nu plus alpha t by nu. Okay, so now what do? I define this whole quantity as t plus. So t plus is defined as equal to rho Cp u star into t wall minus t divided by q wall. If I define this as t plus, then what happens? I'll get dt plus by dy plus is equal to 1 over, this will be 1 by PR because it's alpha by nu, and the other one I'll write it as alpha t by nu t into nu t by nu, so it will be 1 by PRT multiplied by nu t by nu. Okay, let me write that clearly so that it's visible. Nu t by nu. Okay, so this is your temperature profile for the inner layer. Okay, or the thing. So this now can have two parts in the boundary layers. So I can integrate this to get the temperature profile. If I have to integrate this, I have to integrate this in the laminar sub layer, or rather in this case the conduction sub layer, where the molecular conduction is predominant or alpha is predominant, and in the outer region or the core region where alpha t is predominant. Okay, so the thickness of that layer is going to be different from the viscous sub layer. We'll determine that as well in this particular case. So dt plus by dy plus is equal to 1 over 1 by PR plus 1 by PRT. What is PRT? It's actually nu t by alpha t, which is basically the turbulent eddy diffusivity divided by turbulent viscosity divided by turbulent thermal diffusivity. So this multiplied by mu T by nu. Okay. So this is nothing but alpha by nu, and this is alpha T by nu. So this, if I integrate from a 0 to any y plus, then I should be able to get the expression for this. So I don't integrate this, but actually I integrate the other expression. So I take the y plus onto the other side. Dt is equal to, this is dy plus divided by this. So this I integrate from 0 to y plus, and this also I integrate from 0 to y plus. Now what do I do? Again, in the thermal boundary layer, I look at two parts. One is the conduction sublayer, where alpha is much greater than alpha T, and within the inner layer there is a core which is alpha T, which is much greater than alpha, which is also valid here. So this is your inner layer region where the present expression, this expression is valid. That is, you can neglect the inertia terms and you can write this. That is valid in the inner layer. And in the inner layer you have what is called the conduction sublayer, or called the CSL. Just like you had the viscous sublayer VSL there, you'll have a CSL. So I would have y plus equal to 0 to y plus CSL. I'll have alpha much greater than alpha T, and y plus greater than y plus CSL, y plus greater than y plus CSL. I'll be able to say alpha T much greater than alpha. So if I do that, then in the viscous sublayer or conduction sublayer region, this term is much larger than this term, and in the remaining region, where the core region, this term is much larger than this region, so I can neglect this. So if I do that, I can integrate this in two parts. So the temperature T plus at CSL, y plus CSL, minus at y plus equal to 0, this is 0. So at y plus equal, because it is T minus T wall, so T wall is 0. So this is equal to, so this is T plus at y plus CSL, and okay, so we can actually do it in two parts. Viscous sublayer, y is less than or equal to, or y plus is less than or equal to y plus CSL, then I can integrate from 0 to y plus. In that region, that will be T plus at any y plus is equal to, in this case, this goes off, so there will be only 1 by PR, so the PR is a constant, so it will come out, so it will be just integral of this, so it will be y plus. Okay, so for y plus less than y plus CSL. So T plus equal to y plus is the expression that you get for the conduction sublayer. So this is, let us say, equation 1a. And for the core, I'll get this T plus minus, so this is integrated from y plus CSL to y plus. So it will be T plus minus T plus CSL, which will be equal to y plus CSL according to this equation. That will be equal to the integral from 0 to y plus. This term will be negligible, so it will be 1 by PRT and mu T by nu. And what is mu T by nu? We can actually get it from the expression that we had derived in one of the previous slides. Okay, we actually got it from the okay, so from this expression, we wrote the nu t by nu in one of these slides. Yeah, nu t by nu. The nu t by nu is nu t by nu came out to kappa square y plus square into du plus by dy plus du plus by dy plus. So nu t by nu is here, which is equal to kappa square y plus square into nu into this. So nu, as I take it as it will be kappa square y plus square into du plus by dy plus. So let's substitute that in this slide. So it will be integral from y plus CSL to y plus of dy plus divided by 1 over PRT multiplied by this nu t by nu is kappa square y plus square into du plus by dy plus and in this region the du plus by dy plus is also written from the same expression. Okay, so u plus is equal to 1 over kappa log y plus b is what you have. So du plus by dy plus would come out. So this product will actually come out to be kappa y. Okay, we'll do the algebra as you go as. So this would be actually kappa y. Kappa y plus. Okay, so this is the expression that you would get. So the kappa by Prandtl t is a constant and that can be taken out. So you get the integral would be PRT by kappa multiplied by log of y plus divided by y plus CSL. Okay, so this is the expression that you get. So I can write this expression is in a very similar fashion. This is 2a. So 2a basically is t plus is equal to y plus CSL plus log PRT by kappa log y plus minus PRT by kappa log y plus CSL. Okay, so this is the expression. So this is 2a. Okay, so from experiments we can get the y plus CSL as 13.2, PRT as 0.9, and kappa as 0.4 or 0.41 as we had written earlier. So using that, this t plus would actually become 2.195 log y plus 13.2 PR minus 5.66. This is the expression that one can get. Okay, so at y equal to delta, you get T plus, which is actually equal to T wall minus T infinity into rho u star Cp, okay, divided by Q wall. This becomes equal to 2.195 into log of y u star by, delta u star by nu because y is equal to delta at that location, delta u star by nu plus 13.2 ER minus 5.66. Okay, so this is the expression that we would have. So from this actually you can get the expression for delta u star by nu in terms of the remainder and substitute it into the expression. Now in this expression, since Q wall is usually written as H into T wall minus T infinity, so T wall minus T infinity divided by Q wall will be 1 by H. Okay, so this actually could be written as 1 by H, and there will be this rho. If I write u star as u infinity by u star into u star, u infinity into u star by u infinity, so u infinity Cp into u star by u infinity. This is your conductance side. Okay, so this is equal to the expression that we have. So we can even write it in a more generic expression without writing the numbers. So if I write just 1 over kappa log y plus okay, so making a mistake here. This is equal to this expression as we have here. Okay, so it will be the expression that we have here, y is about Prandtl times y plus CSL plus PRT by K kappa into log of at the boundary it works, this is delta u star by nu divided by y plus CSL. Okay, so because the boundary layer profile, this profile, if I substitute at y is equal to delta, then this would become PRT by kappa into log of, this is delta u star by nu divided by y plus CSL. So these two are combined here. This is the expression. So now if I get from the velocity profile that we already have as u star by u infinity by u star, u star by u infinity is actually equal to Cf by 2 square root of, why is that? Because u star is square root of tau wall by rho. So if I write u infinity, this will be u infinity square. This is nothing but square root of Cf by 2. Okay. So if I substitute for that into this expression and simplify, then I'll actually get this number, which is h by rho u infinity Cp. This is nothing but, let's call it as hx by k, which is the Nusselt number, multiplied by 1 over Re, which is u infinity x by mu, and Prandtl number mu by alpha. So this is Nu divided by Re PR. If you look at this, this alpha is k over rho Cp. Okay, so this x gets cancelled between these two, this k gets cancelled between these two, this mu gets cancelled between these two. So you get a h by rho Cp u infinity. So this expression is nothing but Nux divided by Rex PR, as we wrote here. This is Nux, this is 1 over Rex is PR. So you get, actually, this is what is called the Stanton number, STX. At any location, the Nux by RePR is called the Stanton number. So this expression is 1 over Stanton number. So I take it to the other side and bring things to this side and rearrange. Then I get an expression for the Stanton number. So I get STX is equal to CFX by 2 divided by PRT plus CFX by 2 to the power of half multiplied by Prandtl into y plus CSL minus B times PRT minus PRT by kappa log of y plus CSL. This is the expression that I get. So here, if I substitute for PRT as 0.9 from the empirical data, B as 5.1, we wrote 5.5 in the other expression. 5.1 to 5.5 is the range of values that you typically use. This B is nothing but A into log y plus B is equal to U plus. This is the expression. So this B is, we wrote as 5.5. It's 5.1, 5.5 is the range that you get in the literature. And kappa is 0.41. And y plus CSL is equal to 13.2. So if I put all of these numbers into this expression, I'll get an expression for Stanton number, which gives you the Nusselt number. The other way to do it is also the Colburn analogy. Which is an analogy between momentum transfer and heat transfer, which says Stanton number at any x multiplied by Prandtl number to the power of 2 by 3 is always equal to CF by 2 at any x. So if I write STX would be equal to CFX, which is 0.3703 into REX to the power of minus 1 by 5 multiplied by the STX is this into PR to the power of so PR to the power of minus 2 by 3. Okay, so here this is this. So NUX will be STX into REX PR. That will actually become 0. Okay, CF by 2 is not 3703, but it is about 0.028. Okay, so it will be 0.0288 into REX to the power of 4 by 5 and PR to the power of 1,000. So this is your expression for Nusselt number. So then an expression for Nusselt number can come from here or from here in order to get your heat transfer. So this is the expression or solution for your turbulent boundary layer equation with the simplest of possible profiles, which is the 1/7 law profile for the velocity and the two-layer analogy of the boundary layer. So you have the sublayer and the core. There is always a region between the sublayer and the core where the nu t and nu are of the same order, or alpha t and alpha are of the same order. Then you normally do a three-layer model as we mentioned in the previous class. So with that, we'll stop for this lecture. Okay. And we'll come back again in the next lectures, trying to understand the physical meaning of the expressions that we derived today and their limitations. Okay. So we'll understand that in the coming classes. We'll stop here for this.